Hi everyone, and welcome to another episode of Organic Chemistry with Capadia. Today we are starting a new unit on benzene and its derivatives. It is one of my favorite units, so let's get started. Okay, so let's start off with what benzene is, or what category it falls into. So we have two major categories of hydrocarbons. We have aliphatic hydrocarbons and aromatic. So aliphatic are these open-chained compounds that we've talked about previously. Alkanes, alkenes, and alkynes all fall under those regions. And then now we're introducing a new type of hydrocarbon, which is an aromatic hydrocarbon. These are hydrocarbons that contain one or more benzene rings. They're also referred to as arenes, and so those two terms are interchangeable with one another. They are called aromatic compounds because they smell good, let me rephrase, they don't smell good. Not all of them smell good, they just smell. So a lot of these compounds do have an odor to them, and that is why they are called as such. All right, so let's talk about what this benzene creature is. All right, so history of benzene. So benzene was first discovered in 1825 by Michael Faraday, but it caused an uproar because the formula here suggests that it's unsaturated because it's got 6 carbons and 6 hydrogens. So that means that it's not going to, that means it doesn't have the full number of hydrogens that it can have. Even if it was a cyclic compound, it should still have more hydrogens. So it is an unsaturated hydrocarbon, so you would expect it to behave in the same manner as other unsaturated hydrocarbons, such as alkenes. So they started doing some testing with some benzene and trying to figure out how does it react with things. So what they find was that alkenes can undergo hydrohalogenation. If you tried to take benzene and do that, there was no reaction. Hydration is when we add water in the presence of a acid to produce an alcohol. Tried to do that, no reaction. Halogenation, you add a halogen, the presence of a catalyst, and no reaction. Hydrogenation, where you add hydrogen in the presence of a metal. And this was not non-reactive, but it was just very slow and only at high temperatures. And so what that means is that if it was in fact an alkene, it would behave like an alkene. Like all of these reactions are ones that we talked about in the last unit that are common reactions of alkenes. And yet here we have this benzene ring that is supposed to be an alkene, and it doesn't react with any of these and it doesn't undergo any of these reactions. All right, so let's fast forward about 50 years. In 1872, Frederick Kekulé proposed, there's supposed to be a little thing in front of there. It's a accent. Frederick Kekulé proposed a structure for benzene where the double bonds were constantly shifting. So we have here a benzene ring. So it's 6 hydrocarbons and there are 3 double bonds in it. All right. So if we number these 1, 2, 3, 4, 5, 6. So what he said was that there were also this structure where the double bonds had shifted over one. So if we number our carbons again, then it said that our 1 to 6 shifted to 1 to 2, 2 to 3 shifted to 3 to 4, 4 to 5 shifted to 5 to 6. So there was a constantly moving electrons, so the double bonds were going back and forth. So the placement of the double and single bonds was constantly changing, and that would explain some of these issues that they were having with benzene, which it did, but it's still there's still double bonds here, so why isn't it reacting like other alkenes? What is the issue here if there are double bonds? Okay, so fast forward another 50 years, and we get Linus Pauling, who suggested that instead of these electrons moving from single bonds to double bonds, they're actually evenly dispersed. So this is very similar. So our structure actually looks very similar to what Kekulé's structure looked like. But instead of saying that these electrons were moving back and forth between single and double bonds, that they were actually evenly dispersed everywhere so that all of the electrons were constantly moving around the entire ring. So instead of having 3 singles and 3 doubles, you actually had 6 1.5 bonds. So each of these bonds was actually 1.5 in length instead of having 3 single bonds and 3 double bonds. So this is no bueno, and this is what we have. So doing some more experiments and measuring the bond length of the bonds in benzene found out that all of these bond lengths were in fact the exact same length, and therefore this is what Pauling said was correct, and benzene does in fact have an even, all 6 bonds are exactly the same length instead of having 3 doubles and 3 singles. And so what this does is this created an added stability, which is what makes benzene such a strong, capable molecule here. And it explains also why it doesn't behave like alkenes, because in order to behave like alkenes, you have to have an actual double bond that can be broken apart, but there is no double bond here. Like, since all of the bonds are evenly distributed, it's super, super tight, and those electrons are not going to easily leave those bonds. So we end up with this lovely structure, and it explains why it is that benzene doesn't react like alkenes, because it's not an alkene. It's a whole brand new thing. So here we have benzene. So benzene is C6H6, and it's got 6 carbons. I meant to draw the carbons here. 6 carbons, and each one of them has a hydrogen on it. And then we have established that there is not really a double bond. There's just a bond and a half, which is kind of difficult to draw. So we usually, when benzene is drawn, it's drawn with the alternating double bond rings, or the alternating double bonds. It's also very commonly drawn with just a ring in the middle. Benzene shows up a lot, and so it's just a lot easier to draw it with the ring, or you can just draw it with the double bond. Either one is fine. What you cannot do is draw like this. You can't make a whole bunch of dotted lines there. It's not an accurate representation. So either one of these drawings of benzene is fine. You can alternate the double bonds however you want to. Everybody kind of knows what they're talking about everybody knows what you're referring to whenever you draw either of these structures. All right, so benzene is our most common aromatic compound. It is the basis of all other aromatic compounds. Every other aromatic compound is some derivative of benzene, or most every other aromatic compound, I should say, not all of them. All right, so we have what are called monosubstituted benzenes, where the benzene has a substituent on it. We're going to talk about a new substituent group here, which is the nitro group. It's the NO2 group. So anytime that you take benzene and you put a substituent on it, we just call it whatever the name of that substituent is. So for naming benzene, everything is just blah, blah, blah benzene. So here, this is a nitro group, NO2, so this would be nitrobenzene. And so there's no need to number it if it's only one substituent, because like if it's one substituent, it doesn't matter where you put it, it's all exactly the same. And so anything that you've got on here, we can also say, like here, if we have that, this is an isopropyl group, so this would be isopropyl benzene. All right, so benzene is a little bit different from other hydrocarbons in terms of the naming of it. There are a handful of compounds that are monosubstituted benzenes that have common names that the IUPAC has accepted as being official. So, and there's no like rhyme or reason to them, you just have to know them. So let's talk about what these guys are, because we do need to know them. All right, we'll start off with toluene. I'm spelling it wrong. Toluene. All right, toluene is a benzene ring with CH3 on it. And then next we have phenol. which is a benzene ring with an OH group on it. And then we have styrene. So now we're getting into the more complex things. It's got an alkene. It's got ethylene attached to it, an ethylene group. And then we have, next up is aniline, which is an NH2 group on it. And then let's move on down here to a couple of things. So we haven't really talked about aldehydes and ketones in our studies, but we do know what those groups look like. So we've got, this is an aldehyde, so it's got an aldehyde attached to it, so that's benzaldehyde. And then we also have benzoic acid. Benzoic acid. So we have C. And then it's just attached to this benzene ring here. And then our very last one is anisole. Which is when you have an ether that's attached to our benzene ring. Well, it's not really, yeah, it's an ether. It's not attached to the benzene ring, but it is just an ether. All right, so these are our common names of all of our, there we go, all of our benzenes. I can't make this do what I want it to do. All right, so let's make it bigger. Okay, there we go. So these are the common names that we do need to know for benzenes because they are named as such. So anytime that we are looking at any of these monosubstituted benzenes, the names of these benzene compounds are named after these, are given these base names instead of having the name benzene. So like toluene, you'll never see methylbenzene written. It'll always be written as toluene. All right, so we can do, so in the case that you have, so if we have a monosubstituted benzene, then we just name them after these. If there's none of these groups on here, then we just name it as a benzene. In the case that benzene cannot be named easily, then that benzene actually becomes what's called a phenyl group. So if the we can't easily name it, then we consider it to be the phenyl group, and the phenyl group is either written as, sometimes they write it as, there we go, C6H5, or you'll also see it just as this. And usually it's drawn sideways. It doesn't always have to be. But like if we are looking at something, you know, complex, like, let me draw this. There is no name for this right here. Like this substituent here doesn't have a name, right? So now instead of naming it as the something benzene, we call this a phenyl group. So if we count, we have 1, 2, 3, 4, 5, 6, or we have 1, 2, 3, 4, 5, 6. So we'll go 1, 2, 3, 4, 5, 6. And so again, we name them in alphabetical order. So this would be 5-bromo, 1-phenyl, hexane. And it's phenyl sounds like phenol up here. So it's just better if you write it instead of saying it. So yeah, that's what that is. Okay. So what happens if you have two substituent benzene? So if you have two substituents, then you use the special names wherever you can. And then we use special notation to indicate the relative positions. So the three things that we use are we call ortho, meta, and para. So we'll just do a very simple sort of methyl groups here. So if I have methyl on, let's do this. So we'll start with 1 and then 2. So if they're next to each other, this would be called ortho. And then this would just be methyltoluene. Methyltoluene. And then you can also just abbreviate it as an O-methyltoluene. And that works just fine. And then you can also have the meta position. So meta would be the 1 and 3 position. So you have 1 here and 1 here. So this would be meta methyltoluene. And then again, if we want to abbreviate that, then a lot of times it's just written as M-methyltoluene. And then the last one would be para, which is in the 1 and the 4 position. And so this would be para-methyltoluene or p-methyltoluene. All right, so we have ortho, meta, and para. And so instead of calling them, like one, or instead of saying, it would be 2-methyltoluene or 3-methyltoluene or 4-methyltoluene, we would just say ortho, meta, and para. So anytime that you have two substituents on your benzene, you use the ortho, meta, and para distinction. For the common disubstituted benzenes, the only one that we look at is the methyltoluene. So this does have a special name. This is called xylene. So this would be ortho xylene. This would be meta xylene. And then this would be para xylene. And so this is the only disubstituted benzene that we need to worry about. Okay. If we have 3 or more substituents on our benzene, then we use the special names as possible and we just number them in the smallest order. If there are no special names, then you do exactly like we did with cyclic hydrocarbons, where you just number them to give the lowest possible overall numbers that we have. So one of my favorites, so here we do have this methyl group here, so this would be toluene. And then if I number them, I don't need to number the first, I don't need to say that it's 1 toluene, because if it's the special name, then it's indicated that the special named thing is on the first carbon. There's be 1, 2, 3, 4, 5, 6, or you can go the other way, 2, 3, 4, 5, 6, doesn't make any difference. So this would be 2, 4, 6, trinitro-toluene, trinitrotoluene, TNT. So that is that's what TNT is. So it's your most basic explosive that you have. All right, so if you have something that doesn't have a special name, so for example, if we look at, all right, so what we would do is we would number it to give us the lowest combination and then put them in alphabetical order. So I can go 1, 2, 1, 2, 3, 4. I can go 1, 2, 3, 4, 5. I can go 1, 2, 3, 4, 5, 6. That's not going to be it. 1, 2, 3, 4. Oh, that's it. That's the one. Or 1, 2, 3, 4, 5, 6. No. So 1, 3, 1, 2, and 4. Right? 1, 2, 3, 4. All right. So if I name these in alphabetical order, this would be 2 bromo, 1 ethyl, 4 nitro, benzene. Hip, hip, hooray. All right, and then the last thing that we have are what we call polynuclear aromatic hydrocarbons. These are compounds that have two or more benzenes fused together. They're also called polycyclic aromatic hydrocarbons. They're abbreviated PAHs. All right, so under here we would have, so there's a couple here. I'm just going to draw these examples. You do not have to know these. This would be a benzene with another benzene here and here. This is called naphthalene. This is what makes mothballs smell like mothballs. And then we have, if you have three of them, then this is anthracene. And it just goes, I think, there we go. So this is anthracene. And then, yeah. So these are just two examples. Polycyclic aromatic hydrocarbons became very, very popular is the wrong word, but notorious, I suppose, because the first cancer-causing agents or carcinogens were polycyclic aromatic hydrocarbons. So the very, very first thing that we found that created cancer was this guy right here. This is benzoapyrene, this compound here. It is created by the incomplete combustion of certain hydrocarbons. So it's found in things like cigarette smoke, automobile exhausts, and charcoal broiled meats. So anytime that you have anything that can undergo combustion, an incomplete combustion creates these polycyclic rings. And then why is it so dangerous? Well, what happens is when your body consumes these, enzymes try to make these into a water-soluble compound, and so these the enzymes in your bodies convert it into things that have these OH groups on it. It's a diol because it's got two alcohol groups, or it's a double alcohol, like kind of like dienes. And then this O right here, this is what we call an epoxide. This is actually interferes with this is actually a DNA altering compound. So it interferes with your DNA and it causes it to mutate, which creates these cancer cells that are they replicate over and over and over again that we can do nothing about. So that's a fun note. So we will not end on that note, but instead we will do some examples. Hip hip hooray. Okay, so let's look at our compounds here. So if we look at this first one, we first look for special things. So if we look for a special thing, this is a CH3 group, so this is toluene. And so this would just be and so if we look at the two substituents, one is on this is on the 1 and this is on the 4. So this would be para nitrotoluene. All right, if we look at the second one here, we've got two benzene groups here. So this, right here doesn't have a name, like that's not a substituent. So I can't name this as a benzene. I would have to name it as an alkene because it's got that double bond. So it's got two carbons here, and then to the carbon I have attached these guys here. So this would be ethylene, and then I have 1,2 diphenyl ethylene. And then if I look at the way that this is designed, this is going to the side, and this is going to this side. So this would be trans, if we are being super duper specific. Trans. 1,2 diphenyl ethylene. Sorry, 1,2 diphenyl ethylene. All right, let's look at this next one here. So we can see here COOH, that is a carboxylic acid group. So this is our benzoic acid. And so we've got 1, 2, 3. This is in the 1 and the 3 position. So this would be meta chlorobenzoic acid. All right, a couple more examples here. If we look at this, we have more of this. So this is toluene, and this is bromine. This is 1, 2, so this would be ortho bromo toluene. And then here we have 2 substituents. Both of them are methyl groups. And so this is our one special substituent that we need to, this is our one special disubstituted benzene that we need to know. This is xylene, and it's in the 1,3 position. So this is metaxylene. All right. And then we have, what do we have going on here? This is going to be, this should be an O here, NO2. So we have 2 NO2s here. So we have, this is right here. This is CH2CH. So this is styrene. So this is 3 things. So I have to specify 1, 2, 3, 4, or 1, 2, 3, 4, 5. So I'm going to do 1, 3. So I'm going to do 3, 4. So this would be 3, 4 dinitro styrene. All right, moving on. This is OCH3. So this is anisole. So we've got a fluorine group here. They are across from each other, 1, 4. So that's para fluoro anisole. Anisole. And then we have here, this is a very complex, fun-looking guy. So here, this is a CO bond, so this is an aldehyde, so this is benzaldehyde. And then I've got some isopropyl groups coming off of that. So I have 1, 2, nope, what are you doing? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're evenly spaced apart, so it doesn't matter which way I count from. So this would be 2, 4, 6 tri-isopropyl benzaldehyde. Benzaldehyde. All right, 2 more here. We've got 2 substituents. This NH2 makes this aniline. So this is in the ortho position. So this would be ortho nitroaniline. And then lastly, I have this dude right here again, which is like this substituent is nothing real. So I'm going to have to name this after the ring. So this is a double bonded ring. So I have 1, 2, 3, 4, 5. That's it. 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. So I got to go to the 5. And then the double bond would be a 1 here. So I'm going to count this way. All right, so this would be, this is a phenyl group, and this is a methyl group. So this would be 3 methyl, 1 phenyl, 1 pentene. All right. Okay, so that is the structure and naming of aromatic compounds. This has been another episode of Chemistry with Capedia, Organic Edition. I hope you learned something, and until next time, keep on chemin'.